The coronavirus pandemic had an immediate economic presence upon its arrival to the world. Australia, for example, entered a technical recession with GDP declining by 0.3% and 7% in this year's first and second quarters respectively. While responses to preventing its spread has been varied across the world, what has been consistent has been a change in how people have socially organized themselves. One key response in Australia was to enforce restrictions on social interactions, effectively inducing a nationwide lockdown. Importantly, the lockdown encouraged businesses to adjust their working arrangements towards a more remote setup, while people were also encouraged to stay home. With less office spaces being used, more people working from home, service-based businesses seeing fewer in-house customers, and people choosing to stay home, we may see a change in electricity consumption. What we wish to explore in this presentation is how the national lockdown enforced on the 16th of March has affected electricity demand in New South Wales and Victoria. By evaluating its impact on demand, we further wish to provide a model to see the impact of demand on electricity spot prices. We will address this by looking at three sub-questions. Did the coronavirus have a significant impact on energy demand? Did it have a significant impact on demand forecasting? And does energy demand explain energy prices? We will start by looking at the Australian Energy Market Operators Methodology paper. The AEMO has outlined how they modelled demand and created forecasts on the national electricity market. In their model, demand is broken down into two components. Their business demand involves large industry and small to medium enterprise consumption, while the residential demand is household consumption. The AEMO's methodology for short-run electricity forecasting is a linear regression of demand on variables for weather effects. HDD measures the difference between a critical temperature and the actual temperature when it is below that critical value, while CDD is the actual temperature above that critical value. Additionally, there is a dummy variable for non-weekend days. The scatter plot demonstrates the rationale behind the model, with energy consumption changing at different temperatures due to the use of heating and cooling devices, and that overall, electricity consumption is lower on weekends. Ultimately, the AEMO models current electricity demand measured through electricity consumption as being impacted by how businesses and households react to changes in temperature in real time on weekdays and weekends.
Moving on with literature review, we have a paper by Siganthi and Samuel in 2005 that analysed a variety of energy models for demand forecasting, one of them being the AREMA and seasonal AREMA models, which are really useful in measuring elasticities, particularly price and income elasticities within time series data. They quote two papers that are particularly relevant to forecast day-ahead electricity prices and model electricity demand loads using AREMA and seasonal AREMA, as well as GARCH models, which, although are predominantly used for volatility forecasting, there have been an increasing utilisation of GARCH in time series. And Fata, Azine and Aman 2018 speak of the use of eGARCH and the superiority of this model relative to the standard GARCH model, particularly with nonlinear time series and asymmetric demand effects. Next, we have electricity spot prices, a paper by Veronin et al., which develops a variety of hybrid models used to predict and forecast electricity spot prices. They have deliberated that the seasonal AREMA X and ARMA X models, which are just seasonal AREMA and regular ARMA with the addition of extra explanatory variables, are useful in yielding the best results for normal price range. However, we see that simultaneity is present here, particularly that demand being an independent variable and price being the dependent variable. So it talks about the use of the vector auto regressive model to address the problem of simultaneity. And this can be directly applied to our methodological question to examine the simultaneity between energy demand and price data. Next, we have the Chow test, and this Chow test is used to determine whether the regression functions are the same at a certain cutoff point in the data. And for us, in the context of our question, we use the March 16 lockdown date as our cutoff. So starting with an original model, we split this into two different equations, one where C is equal to 1 and one where C is equal to 2. And Wooldridge in 2016 touches on the use of splitting the model into two separate equations to determine whether the coefficients across the two linear regressions are statistically different or are the same. However, this is only valid under the homoscedasticity assumption.
Power demand data and recommended retail prices were collected from the AEMO website. AEMO records power demand and recommended retail prices every half hour. The total demand for each day was generated by summing the half-an-hour demands over the day, whilst the average recommended retail price for each day was calculated by simply taking the average of every half-an-hour spot price. Weather data was collected from the Bureau of Meteorology website. The data was collected from both the Sydney Airport Station and Melbourne Airport Station. Our models assume that this data is indicative of the weather for the entire state of New South Wales and Victoria, respectively. Non-working day data was generated by us by making a for loop which placed the value 1 in every single weekend date.
The model proposed by AEMO regresses total power demand on heating degree days, a variable that measures how much colder than a critical value the day was, cooling degree days, a value that measures how much hotter than a critical value the day was, and non-working days, a dummy variable that takes value 1 for every non-working day. Child tests were conducted for both New South Wales and Victoria. In both cases, we reject the null of a statistically insignificant breakpoint at the first day of lockdown in favour of the alternate that there was indeed a breakpoint at the first day of lockdown at the 5% level. When estimating the model with the lockdown parameter added in, we indeed see that in both cases, beta 4 is negative, indicating a decrease in total demand post-lockdown. This is statistically significant when looking at its HAC p-value in both cases. When looking at the seasonality function model, we regress total power demand against a linear trend as well as a cosine and sine functions for both weekly and yearly seasonality in the model. When conducting chow tests for both New South Wales and Victoria, we reject the null hypothesis of an insignificant breakpoint in favour of the alternate hypothesis that this breakpoint was indeed statistically significant at the first day of lockdown at the 5% confidence level. When estimating the model with the lockdown parameter added in, we again see that total demand has decreased after lockdown. However, when looking at the HAC standard errors, we see that this increase is statistically insignificant. When looking at Bayesian information criteria, we find that the optimal AR model is an AR12 model. A chow test was conducted for both New South Wales and Victoria. In both cases, we failed to reject the null hypothesis of an insignificant breakpoint at the 5% confidence level. This indicates that the model has not changed with lockdown. When estimating the model with the lockdown parameter added in, we again see a negative effect of lockdown on power demand. However, in both cases, we failed to reject the null hypothesis of insignificance of the lockdown parameter when looking at HAC standard errors.
Having analysed the influence of COVID on energy demand, we then turned our attention to the impact on energy demand volatility and forecasting. To evaluate this, we used our best fitting AR12 model from earlier in order to fit the AR12 EGACH11 model to our demand time series. Before we dived into this model, we first tested for the arch effect using the box test. The residual plots on the left here showed some interesting results with some of our A2 components periodically showing very large values. The box test set at a lag of 10 did show that the demand series for both New South Wales and Victoria here on the right-hand side exhibited a statistically significant arch effect. As mentioned earlier, the conditional heteroscedasticity model that we used for volatility forecasting was the AR12 EGACH11 model of the following specifications shown at the top here with our conditional mean and variance models. We chose an EGACH specification over the standard GACH model As per literature in the energy demand sector, which expressed the need to allow for the ability to capture non-linear data, as well as asymmetric effect in past standardized shocks on log volatility, which is captured in the G function here. Our estimation results are as follows below. This was computed using a hybrid solver and a student T distribution for the conditional density of the innovations. We also note here that the estimate for gamma 1 is statistically significant for Victoria, but not for New South Wales, which may suggest that the EGACH is a more suitable conditional heteroscedasticity model in Victoria. Finally, we analyze a forecast of the EGACH across both states. The top diagrams here show how the unconditional sigma forecast appears to revert to the unconditional standard deviation in the long run. Well, interestingly, the bottom diagrams here show that the GACH model, in fact, fits very closely to the actual realizations. The lockdown had a very modest effect on our energy demand forecasting ability. And the beginning of the forecast horizon was established at the early days of the lockdown in mid-March. And we see that the forecasts via this model were able to closely track the actual realizations, further giving us comfort in the AR12 EGACH 11 specification in forecasting and modeling energy demand volatility.
To explore the relationship between price and demand, we decided to go with a vector order regression approach. Now, the first step of this approach is to determine if there is Granger causality in the relationship between price and demand. And we can see that we can confirm Granger causality in both New South Wales and Victoria in both sides of the equation, price affecting demand and demand affects prices. The second step was to fit the VAR model, and we chose the appropriate lag orders by looking at the BIC. Minimizing the BIC, we see that in New South Wales, we have 29 lags, and in Victoria, we have 15 lags. And estimating the model, what we see is that R squared is a lot higher for when the demand variable is the dependent variable. And this is both true in New South Wales and Victoria. Moving on to the impulse response functions, what we see is that there's notable impulse response from demand, but not from price. So we can see that in the top panel, when there is a shock from demand, that shock lasts for quite a while, more pronounced in New South Wales. But when price is the shock, it did not elicit a significant response from demand, but it did affect its price lagged values of prices did affect prices in the future. And this is confirmed by the variance decomposition, where we see that the majority of the variance of demand is explained by demand itself, with some price impact coming in the long term. But for prices, we see that there is a more 10% variation is explained by demand. So in conclusion, we really wanted to answer 3 key questions today. So firstly, did COVID have a significant impact on energy demand? And we find that the Chow test says that there is a significant change, or except in the AR model. Using hack standard areas, we find that the effect of the lockdown is only significant under the AMO approach, which we conclude that lockdowns have modest effects in accordance with the AMO findings. Secondly, we looked at, did COVID have a significant impact on energy demand forecasting? Loom box test reveals significant arch effects, but we find that overall, there's little impact on lockdown on forecasting ability. So in conclusion, lockdowns have also a modest effect on energy demand forecasting abilities. And lastly, does energy demand explain energy prices? Now, because of Granger causality, we fitted a vector order regression model, and we find that impulse responses from demand was much more significant than prices, although there was some price impact on demand in the long term, where demand contributes 10% to the price variation. So the key takeaway here is that demand shocks contribute mostly to the responses. Thank you for listening, and we hope you enjoyed this presentation.